Thank you. Let me begin with the outline of the talk. So at first, I'll begin with the principle of operation of fiber optic communication systems we are currently using to communicate over internet. I'll point out where the security gap is and how potentially QKD could solve problems of privacy we already have. Later on, as QKD is a very broad topic, I will focus just on QKD implemented in time and frequency. And finally, I'll discuss the potential and opportunities for photonic integration and potential for infrastructural implementations of such systems. Starting with fiber optic networks. In this picture, you can see an exemplary QKD network. And that network consists of multiple lasers. So what's happening right now as we are attending this seminar? Our computer produces many bits of information, so high and low voltage signals, which somewhat need to be converted into optical signals that must be distributed over fibers to a distant location and possibly back so we can decode that information. So every piece of such thing starts with a laser diode operating in a continuous wave mode. And this serves as a source of optical carrier, which then is used as a medium we can modulate using electro-optic modulators and inscribe information as zeros and ones we use to talk to each other right now. And in order to deliver information to a very specific place, we need multiple lasers and multiple modulators separated by some frequencies so that actually we can distinguish them. And in order to transmit them some far away, we pack all the signals using a multiplexer into one optical fiber. As there are losses in the fiber, we amplify that signal, then we split it, and then finally photodiode converts optical signal back to electrical so we can actually communicate. And how do we inscribe those ones and zeros? Well, electrically, as you can see on the top of the first picture, you can see the square wave representing ones and zeros, high and low voltage signals, and a carrier wave. And one of the techniques to inscribe those zeros and ones is called frequency shift keying, which means we actually change the frequency of the carrier so that it may represent 1 or 0 when frequency of the carrier gets higher or lower. This is just one of the methods. We could also use time domain and think of some sort of reference like a clock signal, like the rectangle, and actually discriminate pulses arriving at different moments of time, either earlier or later, and assume that the earlier one means 0, the pulse that came later means 1. This is called pulse position modulation. But there is an issue. There is a major security gap. We send some bits of information using millions of photons originating from the laser light sources. So it is not a problem to couple into such fiber and actually grab a few of them, getting 100% of the information. And to those information belong our cryptographic keys. We actually use every day, maybe without noticing, to secure our bank transcripts, our PIN codes, our account numbers, and maybe we could or should use in order to protect our intellectual properties, like maybe some drafts of papers or some important results. And unfortunately, there exists a device which is perfect for that. It is called the Clipon coupler. You can see it here. This is just a prism that allows you to couple light into a fiber, and the principle behind it is the evanescent coupling through the base of the prism. And let me read parts of the definition to realize how dangerous the tool is. It is designed for bidirectional and full duplex signal coupling on single mode fibers, provides non-intrusive and non-damaging optical coupling. It does not require access to the fiber end and is ideal for temporary connections between fiber and instrumentation or communication devices, namely spying. So a typical hacking scenario would look like this. There is a sender called Alice with a sequence of bits, may that be our PIN code or some cryptographic key we need to transmit, and a receiver, Bob, and a hacker called Eve. So Eve would ideally place a clip-on coupler between Alice and Bob. That could be thought of as a simple beam splitter, and she can get the exact copy of data simply by splitting the laser beam. And this kind of attack is called man in the middle. But what if we change that approach and actually, instead of sending one bit of information using multiple photons, used only one photon to transmit one bit of information at a time? And moreover, single photons reveal quantum properties we could potentially use to detect the presence of the hacker in advance instead of trusting our security solutions. And so we can actually take a very different approach to security than we have so far. So we can distribute a key in a safe manner and listen for the presence of the hacker. And had that hacker been present, we would never have used the key. What does exactly this procedure look like? Let's discuss it on the first QKD protocol called the BB84. BB stands for Bennett and Busser, the inventors of that technique. In order to perform such distribution of the key, we need single photons, and we need some information system. So we need to assign a bit value to the polarization of the photons. So may the horizontal polarization mean 0, may the vertical mean 1, may the diagonal, anti-diagonal mean 0, diagonal mean 1. And let's observe that those states form bases, and those are mutually unbiased bases. You can represent any of the photons as a superposition of the two other from another basis. That's crucial in order to detect the presence of the hacker. I'll mention that in a minute. So the procedure of key distribution is such that Alice randomly picks a bit of information to be sent and the basis. She remembers that twice and sends single photons to the receiver called Bob. Bob also randomly chooses a basis and remembers both the measurement outcome and the basis he chose. Now, in order to keep the bit of information, the basis that was used for sending a single photon state must be the same as the one used for measuring that state, simply due to the fact that had a single photon from, let's say, HV basis been measured in the DA basis, we cannot perfectly say what's the meaning of that photon, what's the bit it carried, as the measurement outcome will be one of the basis vectors with equal probability in this case. So let's observe what the procedure looks like on a simple example. Let's assume we want to send binary 1 as a diagonal photon, and so we do. But the basis used for measurement was the HV basis. So with some probability, Bob measured 0, but this is not a compatible basis, so we reject that bit of information. Now let's say we send 1. We've used, again, HV basis for measurement. We indeed have measured 1, but we keep that bit of information. And after many, many bits, we actually can see that we get a random bit string, which can form a cryptographic key that was perfectly exchanged without any risk. Why without any risk? Due to the fact that you can see that many bits are erroneous, and we can compute those statistics and check for how many bits were erroneous within the transmission process. This is called QBER, quantum bit error rate. And in presence of the hacker, which would ideally like to measure a single photon, reproduce the quantum state, resend it, and force the receiver to measure the same quantum state, will introduce errors as well. So if our error rate is too big, we conclude that there was a hacker present, and we never use the cryptographic key. So we are never endangered. Recent 3 years is the time of a rapid development of such techniques and multiple implementations, which seem impressive. One of such examples is Toshiba Cambridge City Network, where Toshiba scientists constructed a prototype system based on phase encoded BB84 protocol, in which they also sent 1 bit of information per 1 single photon, using 2 decoy states to additionally increase the security. And what they managed to achieve is they connected 3 different institutes in Cambridge. You can see the distances and fiber attenuations in here, achieving 2.22 megabits per second of secret E-share rate. And what's even more impressive is that those qubits were sent along regular network traffic in a WDM system. China and Vienna were fortunate enough to have their optical seminar encrypted by means of QKD, and cryptographic keys were exchanged with satellites. You can see the qubit rates were significantly lower, but when exchanged for a certain period of time and held in a safe manner, they could actually secure an hour-long video conference. So yes, they have quantum secure Skype. In Poland, there is also it is also a topic of interest. So Piotr Wichowski from the Poznań Supercomputing and Networking Center has recently launched a link in a Poznań City network. That was a commercially available system from ID Quantic, Clavis scientific system, which provided 2.2 kilobits per second of secret key rate over approximately 65 kilometers of fiber. I have slightly highlighted that we send 1 bit of key per 1 photon, but it does not necessarily have to be this way. Actually, the tunnel capacity would be way greater if we sent more than 1 bit per photon. So if we used symbols instead of bits. So in order to construct a symbol, we would need a multidimensional quantum state. And the benefits are, according to the analysis of Genovese and Tirana, that it will provide us with increased robustness against the noise and higher secret key rate. So now gathering all the ideas, let's think how to implement frequency shift keying in QKD, increase the dimensionality, so not to send simply qubits, but QD-dimensional bits, Q quarts in this case, and thus enhance the capacity of the channel and its resistance. So in the classical way we thought of changing the carrier frequency, we may think now of measuring central frequencies of single photons. And we have a certain probability distribution, Gaussian in this case, also for a reason, to catch single photon within that interval of frequencies, so within this spectrum. And may different central frequencies represent different sets of bits of information. So we can actually, using 4 symbols, we could send 2 bits at a time. So we can implement pulse position modulation. This time we'll think that we have a certain reference point, like a clock edge, and measure the delay with respect to the clock edge of single photon's time of arrival. And different delays indicate different bit values. But security is another thing. In case of polarization, if we try to measure a vertical photon in a diagonal anti-diagonal basis, we would get either diagonal or anti-diagonal outcome with 50% of chance. So there must be a chance for a hacker to make that mistake. And how to provide security of encoding in time and frequency case. Fortunately, time and frequency are related to each other via Fourier transform. So there exists a limitation, a sort of Heisenberg uncertainty principle. And the time bandwidth product between spectral and temporal Gaussian function is well known, indicating we cannot exactly measure both at the same time. And it turns out that selecting a certain ratio of pulse separation and width, temporal and width, FWHM width, by width I will mean through all this presentation the FWHM width, we could set the system in such that if we measured any of those pulses, symbols, in a conjugated domain, it would spread among all other symbols in the conjugated domain carrying no information at all, and vice versa. Such relations were proposed by Rodiger and Perlot and Joshua Nunn and Wright. Those relations dictate that separations, that width of the pulse position modulation symbol pulses should be similar to the separation between pulses, that width of the FSK, which is frequency shifting symbols pulses, should be similar to the separation between them. And the conjugate ppm pulses should be approximately as wild as m, where m is the number of the symbols constituting our coding system alphabet. M is equal 4 in my case. So m FSK symbol pulses and respectively m conjugated m ppm pulses should be approximately as wide as the conjugated FSK pulse. To construct such system, we need sender and receiver. Sender should be granted equipment that can generate FSK symbols, ppm symbols, and it should be equipped with some clock reference. Clock reference will be distributed over a public channel, which is a regular fiber or radio communication system. Could be free space or space as well. So that receiver is synchronized. And via the quantum channel, which again is possibly just a regular optical fiber, we would send those symbols randomly to the basis of measurement and perform either frequency resolved single photon detection or time resolved single photon detection. The first one is a bit of a problem because there doesn't exist an at-hand available optical spectrum analyzer for single photons, for single quantum radiation. So I had to implement a different technique to measure the profiles and central frequencies. And dispersive Fourier transformation came very handy as it enables direct single photon measurements. And the principle is that we use a dispersive medium, that's typically a chip fiber Bragg grating with a circulator, to stretch the pulse in time and thus perform mapping of frequency to time. Resolution is dependent on dispersion. Usually, the greater the dispersion, the greater the resolution of such measurement. And here is an example. If a Gaussian optical signal that is, for example, 100 picosecond broad, wide, would enter a CFBG, it would be approximately 300 picoseconds broad after passing through it. And resolution is approximated based on the Rayleigh's criterion, so I assume I can distinguish the two pulses if the maximum of the first is collocated with the minimum of the second. In my case, the resolution is the 30 picometers, and that's a starting point to calculate other parameters. This is regarding the parameters by Rüdiger, who actually estimated the security and necessary relations between the pulses. So now let's construct a transmitter. Again, as in case of the telecom link, the heart of the system would be a laser diode operating in a continuous wave mode, which is driven by the laser diode driver and the waveform generator to tune the central frequency of the laser. And pulses would be cut using electro-optic amplitude modulator, which is driven by a power supply providing DC bias voltage. And the Gaussian shape of the resultant optical pulses would be created by an arbitrary waveform generator, generating some signal which is amplified to ensure proper depth of modulation. There's a reference clock which is necessary as we need to synchronize generation of the pulses with possible detection. And finally, pulses are attenuated with the variable optical attenuator to the single photon level so that we get a good approximation of single photons. On the receiver side, I have to choose whether I measure in frequency domain or in time domain. In frequency domain, this is a dispersive Fourier transform. So photons are being stretched in time. They're being detected by ultra-sensitive superconducting nanowire single photon detectors, which produce electrical pulses as the photon arrives. And those electrical signals are mapped with a time tagger, which is synchronized with the sender. In time domain, I just detect a single photon and map its time of arrival. Then data are histogrammed and post-processed. That's what a typical histogram looks like. What would be crucial and interesting in this case is the uniform shape of that histogram. The desired one is Gaussian. And to observe if the desired parameters, theoretically computed, are satisfied for all the symbols we construct alphabet of. And the desired parameters are spectral symbol separation, which ought to be 30 picometers, FWH width of those symbols, which should be 35 picometers, temporal symbol separation equal to 21 picometers, their width equal to 25 picoseconds, and measurements in conjugate basis to see if actually spectral symbol, which should be 100 picosecond long, is approximately as wide as 4 temporal symbols, which should be 25 picosecond wide, right? And temporal symbols with in frequency should be equal to 140 picometers, which is 4 times the spectral symbol FWH width. And in this case, the temporal widths, which are approximately 108 picoseconds, correspond very well to that prediction. After a dispersive Fourier transformation, those frequency states seem to be well separated. Again, histograms look pretty equal. Widths look quite uniform, and indeed they are. So we can see that spectral widths are roughly 38 picoseconds out, and the requested value is 35. So that's a pretty good match. And separations are equal roughly to 30 picometers, which is what it should be. In the time domain, histograms again are uniform, are equally broad, are equally separated, are more or less properly separated, a bit more than 21 picoseconds, but unfortunately they are twice too wide. We can see that certainly I cannot apply a Rayleigh's criterion to distinguish the two neighboring pulses as maximum is not collocated with the minimum of the first one, but of the second. So which is twice too big. Why? I'll come back to it later. And performing dispersive Fourier transform on the temporal pulses. Again, good news is that spectra are quite indistinguishable, which is very important for the security of encoding. They are uniformly shaped. However, that shape looks quite nasty, although we could find a Gaussian envelope within it. And the temporal widths in frequency are way too low, order of 40 out of 140 requested. So why is it imperfect? What limits? What stops me from further increasing the dimension of the quantum state and potentially sending more bits of key per one photon? It's the jitter. It's the bandwidth. It's the problem of digital to analog conversion during pulse generator. And it's a finite DFT technique, spectral resolution. Jitter is just a deviation from the original signal's periodicity. So change in a period resulting actually you have some edge of the signal landing in an unwanted moment of time. And resultant jitter is the RMS sum of independent jitters. In the detecting system, a source of the jitter is the time tagger itself, which is imperfect device, and superconducting unaware single photon detector, which is imperfect as well. Both of the jitters give the resultant jitter RMS of 11 picoseconds, and thus FWHM jitter of 26 picoseconds, and no temporal symbol will be narrower than that. Also, bandwidth is finite. Bandwidth problem refers to arbitrary wave generator, high frequency amplifier, and electro-optic amplitude modulator. We can see that 3 dB bandwidth is approximately 16 gigahertz. And I wish it was twice that much at least. Moreover, modulators transmittance is not linear, and the modulators like to thermally drift, and pulse width is strongly dependent on the amplitude of the voltage signal. Gain is also dependent on frequency. So actually something that seems to be a quite simple setup is very fragile to any changes. And as transmission function cuts part of the spectrum, pulse gets temporarily broadened and it gets distorted. This is something I can partially compensate for. So as I know the transfer function, I actually can compensate for the losses in spectral components. This is what I did. So the results involved using compensation. It involves using compensation for the modulator's non-linear transmission as well. And both experiment and simulation has proven that no symbol will be temporally narrower than 34 picoseconds due to bandwidth. Now taking a slight step back and looking at the advantages and disadvantages of the protocol, we could specify that it definitely is a plus that such protocol uses well-known modulation schematics. It can be implemented as a multidimensional version, enhancing tunnel capacity. It is compatible with fiber optic networks, and some experts say that possibly with satellite and free space optical communication. There exists a dispersive Fourier transform technique that allows measurements of single photons profile directly, and it could be implemented using photonic integrated circuits. I'll come back to that later. Looking at the disadvantages, so we can actually tackle them. Timing jitter strongly limits the detection, so does the RF bandwidth, which limits the generation of such states. And finding a compatible resolution, find a compatible set of parameters it's a difficult trade-off. That's a major challenge, as I need to be able both to measure in time and frequency simultaneously, and those are conjugated bases. That trade-off is difficult. So the system require complex and expensive components, and unfortunately, the parameters by Benson are only approximation of security. This protocol still lacks proper security proof. But maybe there is something I could do about those issues. And if I were to address symbol generation issue, I would think of changing the approach. So instead of using high frequency electronics and one modulator, maybe it would be beneficial to use two cascaded modulators and lower frequency signals, which can be controlled in a precise manner. And so had I generated two pulses at two different instances of time using two modulators, the common part, which would make a resultant signal, would be very short. Eventually, I should change parameters of encoding and find a better trade-off between them. or implement time lensing to shorten pulses, both at the detectors and receiver's side. And I highly recommend a paper written here, which is the research of members of quantum photonics laboratory. Now coming to photonic integration. Photonic integrated circuit could solve numerous problems as it offers multiple optoelectronic devices on a single chip, which is just as big as the tip of my finger. You can see it in the picture on the left. So this is a tiny integrated circuit. Those probes are electrical connections we use to drive lasers, modulators, and other necessary equipment. And here you can see a microscope image of it. And we can see that it consists of many modulators, lasers, couplers. So actually, numerous components on the optical table could be packed into something that's as big as a fingertip. Great benefits of that technology could potentially be, for the sake of generating high dimensional pulses, could potentially be using multiple lasers instead of having to tune one. So simply switching a fixed laser on and off, another one on and off to generate pulses and to sweep over it. Also to use multiple modulators of different kinds, like amplitude modulators, phase modulators, to implement maybe time lensing, maybe a different version of QKD protocol, or just very well implement the time frequency QKD. And this is made possible by Institute of Microelectronics and Optoelectronics at Warsaw University of Technology. The purpose of quantum key distribution is actually to enable us safe communication. So I need infrastructure to perform any tests of communication. And fortunately, I have access to University of Warsaw dark fibers. That's a ring infrastructure. This is a schematic of the connection we have at our university. We're here at Ochota campus, and I'm very tempted to send some qubits on the rector's feet through the central campus, perhaps directly to Chorza, and then through the Marriott, which is LIM, to Pioneer Network. The Pioneer Network would also be used in the NLPQT project to construct a QKD link out of commercially available devices, providing me with data to compare and increasing infrastructural potential for further tests of such solutions. I'm also quite looking forward to optical carrier link, which may help to synchronize devices. You can find out more at the NLPQT project website. On the side of theory, the work is in progress, and I wish to appreciate and thank very much participants of the Kyish Quantera project, especially Piera Machiavello, Dagmar Bruce, Ian Wonsley, Christine Zilberhorn, Michał Kolobov, and Michał Karpiński from University of Warsaw for taking up a challenge of proving the security, estimating parameters even more exactly. I'd also like to thank team from the Warsaw University of Technology, especially Dr. Ryszard Piramidowicz and Dr. Stanisław Stopiński from the Institute of Micro and Optoelectronics, Warsaw University of Technology, for their expertise and will cooperate on photonic integrated circuits that could potentially serve for quantum key distribution. And finally, I wish to thank my supervisors, Professor Czesław Radewicz and Dr. Michał Karpiński, the group leader of Quantum Photonics Laboratory, when you can meet experts on quantum optics and spectral-temporal experimental manipulations of light, like Filip Sośnicki, Ali, Golestani, Michał Mikołajczyk, Sanjay Kapoor, and our master students, Arifa, Amalia. Thank you very much for your time.
Thank you, Adam, very much for a very interesting and inspiring talk with many, where you outline not only results, but also problems for the future.